Hello everyone. So today we'll be discussing about simple bending equation. So before that I want to just mention you about the bending stresses. What are the bending stresses and what are the assumptions made in the simple bending theory. Okay. So if a beam is subjected to any kind of external loads, if it is acting on it, so it will be subjected to shear force and bending moment at any section. It can be at the top or bottom. There will be some kind of stresses will be acting on it. So these stresses are induced due to bending moment. The stresses that are induced due to bending moment, it is known as bending stresses. Okay. So these bending stresses will be occurring because of the constant bending moment. If a beam is subjected to a constant bending moment with zero shear force, then it is known as bending stresses. Okay. So here you can see what is this simple bending when just if you have considered a beam with the load of W at the ends of AB length. Okay, so it is subjected to shear force and bending moment diagrams you can see here. So next, coming to the assumptions made in the theory of simple bending. So first assumption is the material of the beam is homogeneous and isotropic. Okay, so what is meant by so what is meant by isotropic? If you see, it means it's of same material. Okay, it is of like we'll be using same kind of material throughout the length of the beam or throughout the section. Okay, next, and it is also isotropic. So isotropic means it means elastic properties are same in all the directions. If it is like x, y and z direction, it is of same. Okay, next assumption, the value of Young's modulus is same both in tension and compression. Next assumption, the transverse cross section which were plane before bending remains plane after bending. So before and after bending, the transverse cross section will be same. When coming to the next assumption, the beam is initially straight and all longitudinal layers or filaments, you can say, bent in circular form. So it will be with a common center with a radius. So it will be having bending in a circular form. Okay, next, the radius of curvature is large when compared to the cross section of dimensional. So you will be saying that the length will be increased. So the radius will be more when compared to the section dimensions. Next, last assumption, each layer of the beam is free to expand or contract independently. Okay, so these are the assumptions made in the simple bending theory. So if we have considered a cross section of a beam of AB CD layers and neutral axis NN and a section of separate section of EF layer with a distance of y from neutral axis, and the distance of the A, C and BD and EF is considered as delta x. Okay, as we know, when a beam is subjected to loading, so always the stresses, whatever the stresses was formed, so at top section it will be formed as a compression and bottom it will be formed as a tension. Okay, so if you have seen the figure A, it shows the part of a beam is subjected to simple bending. Okay, next, if you see the figure B here, so figure B, if you see here, this point it is a deformed shape. Okay, after once the load has applied, how it has formed. So here AB and CD are two cross sections. Okay, AC is the top layer and BD is bottom layer. NN is neutral axis, and what is the length of the AC BD NN is delta x. Okay, next, consider EF layer at a distance of y from neutral axis. Next, if you see the figure B, if you have seen, A dash C dash is a compressed layer and B dash D dash is an expanded layer. You said as bottom will be, it is subjected to tension, right? So it will be expanding, and top it will be subjected to compression. So the layer will be decreased. Okay, and n dash is a neutral axis. So here neutral axis is the point layer where it won't be subjected to any kind of compression or it won't change, it won't expand or contract. So that layer is considered as neutral axis layer or neutral layer, you can say. So next, by using the strain derivations, so if you have considered r is the radius of n dash and AC is equals to BD is equals to NN is equals to EF, that will be of delta x. After bending also neutral axis n dash will be same, that is delta x. If you see from the figure B, so n dash is equals to r theta. So delta x is equals to r theta. So if you have seen what is the increase in EF layer, if you see, so what is the increase, expanded layer minus original layer gives you the increase in the change in the length, right? So E dash F dash value is r plus y into theta and EF value is delta x. So if you see delta L, change in the length will give increase in the length, delta L is equals to y theta. So if you take the strain in EF, so what is the strain formula? Change in the length by original length. So what is the, for EF only EF section we are taking. So what is the change in length? Delta L is y theta divided by L is r theta, original length is r theta. So from this equation, if you see theta gets cancelled, so strain E is equals to y by r. So if from this you can say if strain is increasing, that increases with the, they will be directly proportional to the distance also from the neutral axis. Okay, so hence maximum strains at the extreme fibers, we know that. So at like maximum distance, so at the value will be more. So we know Young's modulus is equals to stress by strain, so that is sigma by E. So sigma is equals to strain into Young's modulus. So from this you can say we know what is strain, E is equals to y by r. Then what will be the stress? Sigma is equals to y by r into E. So this equation we can simply write sigma by y is equals to E by r. So stress, bending stress is maximum at extreme fibers. In case of pure bending stress, so where it will be the zero means it will be at neutral axis. So next, if you see the next part is moment of resistance. So if you have considered again a small layer at a distance of y from the neutral axis, this time we are considering at the top section. So there that dA portion will be considered as the area of the elemental strip, which is considered from the neutral axis at a distance of y. So okay, now the force on the layer, if you see, stress on the layer is equals into force is equals to stress by area. So stress is we have considered as sigma, and what is the area? dA. So moment of force of the layer about neutral axis will be force into perpendicular distance, that is P into y. So we know what is the force, sigma into dA. Then so we are calculating moment. So force moment is equals to force into perpendicular distance. Here force is sigma into dA and perpendicular distance is y. So then that is equals to sigma we will be writing in the full form. So E by r into y into dA into y. So from this we will be getting moment is equals to E by r into y square into dA. So if you see the moment of resistance, so total moment of force of the entire section of the neutral axis is called moment of resistance. So here m is equals to E by r into y square into dA. So if you do the integration for that moment of resistance, so we'll be getting E by r is into y square dA. So this integrated y square dA will be represented as moment of inertia. So moment of resistance m is equals to I into E by r. So m by I is equals to E by r. So this total equation m by I is equals to sigma by y is equals to E by r, where m is equals to moment of resistance, I is equals to moment of inertia, sigma is equals to maximum bending stress. So that will be at extreme fibers. Okay. So y is equals to distance from neutral axis, E is Young's modulus, and r is the radius of curvature of neutral axis. Thank you.